Michael, I can't find your phone number to send you text, so you need to do the syllabus quiz. I don't know why I don't have it saved. That you go to work at, the first thing they're probably going to do is, or they should do is, go through your safety training. Very, very important. Does all employers have to do safety training? Yes or no? Does all employers have to do safety training? Yeah, well, if you go to work in a legal office or something like that, they would be considered. So it's people basically that does manufacturing, right? It deals with manufacturing or repair, right? Or dealing with equipment that could cause problems, right? So I haven't seen anybody that has safety rules on how to use a computer. So the main department is it's a governmental department. It actually has a person that's on the president's advisory board, or what they call the big first group, called OSHA. And what does OSHA stand for? Safety and Health. Association? Then we have the people that establish codes, so we have another one that's basically responsible for electrical safety, and this is called the National Fire Protection Association. We call them NAFTA, right? NAFTA. And a lot of people are familiar with the National Electrical Code. The National Electrical Code is not considered a safety code. It's how to safely install things, right? You understand? It does not protect your safety. These are the two standards we're going to look at. So NAFTA MFPA 70 is the National Electrical Code, but a lot of people don't know that. And then they finally realized that we had to have a code or standards for electrical safety, and that's when they came out with the 70E. So 70E is specifically for electrical safety. And so what could happen to you in electricity? Could be electrocuted. Right. Burn. Well, it's about to say. Well, what they deal with what we call arc flash, arc blast, and then also electrical shock. So they don't deal with electrocution. They deal with electrical shock. If you don't get shocked, you won't get what? Electrocuted. So they show you how to be safe around electrical devices to prevent them being shocked. So OSHA, the main part of OSHA is the OSHA 910. Electrocuted means you're dead. Shock means you're shocked. So you can't be electrocuted unless you get shocked. So a lot of people say NAFTA prevents electrocution. No, the 70E does not prevent electrocution. It prevents shock, right? You understand? So it's a safety to help prevent you between electrical shock, what we call arc flashes, which are caused by short circuits, right? And then arc blast is what is primary concern. So the big difference between OSHA and NAFTA is not law. Normally it's not law. OSHA's law. NAFTA standards are not usually law. But what you'll find out is a lot of the National Fire Protection Association safety standards have been adopted by OSHA. They're in the OSHA standard. But if you like National Electrical Code, is that law? No. Until what we say the authority having jurisdiction makes it law. So National Electrical Code said this is the way you should safely do this work or install this stuff. But as soon as the authority having jurisdiction adopts the code, then it becomes law. You understand that? So we can't say it's not a law. It is a law. It will become a law when Birmingham, when the electrical inspectors in Birmingham adopt the code. Then it becomes what? It becomes law. If they don't adopt the code, then it's what? It's not law. Is OSHA law? Usually OSHA does not apply to companies that don't do internal stuff. Basically, they have to do. I think you have to cross a state line, right? You understand? But what we find out is that almost everybody adopts this because that basically covers themselves if something happens, if an accident happens. So if an accident happens and you don't follow OSHA guidelines or you don't follow 70E guidelines, then you're leaving yourself up for what? Lawsuits, yeah. So basically, what these do is it basically takes it off the. So basically, electrocutions and now people that does OSHA and follows the MFPA requirements is people that get electrocuted. It's their fault because they did what? They didn't follow these safety. Understanding arc flash, PPE. Everybody know what PPE is? Equipment. This is what you wear when you get into a situation where you might get into these problems. Understanding the boundaries and implementing 70E qualified employees. So I just updated this, guys. So 2,652 electrical related workplace fatalities. This is not the number of people that got shot. These are the number of actual fatalities in between 2003 and 2016.
Worldwide?
No, that's here. This is OSHA and National Protection. Yeah, I'd like to know worldwide. This is just here, right? I understand that in the United States. 13,150 severe injury. 80% of all of the injuries are caused by arc flash, which could cause a blast. Are we okay? Makes sense? So this is the number of fatalities and injuries by event code. 2003 to 2016. What you can see the trend since all these safety procedures are coming into play. What's the first thing you notice? And it's declining. So 2016, 2014, 2016. But compared to what we did in 2005, in 2006, and 2004, we're a lot better off than we used to be. Are we okay? Electrical injuries could cause what? Yeah. How could it cause a cardiac arrest? Could cause a lung to collapse, but it could cause your heart to stop or go into what we call fibrillation. What's fibrillation? That's when your valves and the beating of your heart are out of sync with each other. So what that means is your heart is pumping, but you're not generating pressure. So you don't have blood flow. And that's what we call fibrillation. So the heart just goes crazy, and your valves and your heart are not in sync with each other. And that's why they bop you with that high energy or that pulse to try to make everything open and close at the same time, right? Get y'all back in the sync. Respiratory failure, like collapsed lungs, all kind of problems we could have with this. Muscle, nerve, and tissue destruction. We are semiconductors. We have a pretty good insulating layer in our fingers, but if it ever gets through our fingers, guys, you're semiconductor. So if we break down this, if we see what this guy can protect us for our skin, then we have current flow through resistance, and what does that cause? Watts, power. V, P is equal to V times I. Causes your muscles to literally burn up, right? Of course, where does it go? Sometimes it gets into your bones and flows down through the marrow of your bones and destroys your bones, your marrow. Then you're in real trouble because that's where your white blood cells are created, right? Which means now you're going to be very susceptible disease, tissue destruction, burning up things. But what you got to understand, guys, is that 2,652 deaths over this many years is fairly low, right? Y'all understand that 250 people across the entire United States die from electrocution. So if you, it's a trade, right? It's got a danger involved, but if you just take your time and do things the way you're supposed to do, then it's a dangerous career, but there's a lot of hazards. What is a hazard, by the way? A safety hazard. It's something that has a potential to cause an energy. Not an energy, a what? Injury. So that's what a hazard is. It's something, it don't mean it's going to do it, it just has the what? Potential to cause it. And usually if you follow the safety procedures or the safety rules, then that's going to help you to avoid what? Hazards. Right? Or correct hazards too. Hopefully we can correct hazards, but we can't correct all of them, right? I wonder how many people in the United States got killed in traffic accidents during that same year. So it's a lot more dangerous to do what? Get in your car every day, do what? Drive home, right? Than it is to work around electricity. As long as you follow the rules. But it's one of those, if you don't follow the rules, it's going to get you. Right? Cardiac arrest, respiratory, muscle failure and destruction, thermal burns, secondary injuries. What do I mean by secondary injury? If you fall because of it, right? Or if you're up on a ladder and you get shocked and you fall off the ladder, these would be secondary injuries. I don't know where I got that picture up. So electric shock received when current passes through the body. Severity of the shock depends on the path the current goes through, the amount of current flowing, and the length of time the body's in contact with that. Right? Low voltage does not mean low hazard. You understand that? Like your car battery out there. Your car battery might be 12 to 14 volts, but if you short out that battery and it blows up on you, you got big problems, right? There's a lot of energy in a car battery. So car batteries and short circuits will flat burn things up because there's all kind of current. What determines how much current flow you get into the body? What's the formula? Ohm's law, guys. V over R. How much voltage you have divided by the amount of resistance. Right, you understand? So the higher the voltage, the more dangerous it is. Right, you understand? But also the lower the resistance, the more dangerous it is. Right, you understand? So if a resistance goes down, then a lower voltage can kill you. Now what can cause your body resistance to go down? First of all, it's the path. The path, right, could determine your body resistance. What environment you're in. So in Alabama, we have hot, humid days, which opens up our pores, right, and lets salt water come out of us. We call it sweat, but it's salt water. Salt water has low resistance. So if you're sweating a lot, your body resistance will be really, really high. The thickness of your skin, right? Where do we have pretty thin skin at? Yeah, ears has got really thin skin up there, right? Huh? Yeah, but cartilage is inside. It's getting through that skin. So we'll look at some of the paths. So not a fixed quantity. Depends on the path. Hand to hand, hand to foot, foot to foot, hand to hand, elbow to elbow, whether you're wet, whether you're dry, whether you have open units, or whether you get into AC or DC. DC is a little more dangerous. The problem we have is that our muscles are controlled by electrical current, right? You understand that? And if we override that electrical current, our brain cannot the current flow through my arms is greater than the current, like my brain's trying to put out, then we have a tendency to lock on to things. So we grab them when we can't let go. And now you got problems because now you're in a circuit over a length of time, right? You understand? You start perspiring real fast. Your body resistance goes down real fast and you get into trouble. DC is a little more, we're not saying this, but DC wants to hold on to you, right? AC, we go to 0, but it's so fast we have problems. But AC may not grab you as bad as DC will. And that depends on the frequency. So electrical current paths, these are showing you touch. This is very dangerous. And why is this very dangerous?
What do you mean? Why is what?
Yeah, this is one of the most dangerous paths right here.
Oh, I see.
This right here. Passes through your heart. Right, you understand. And your heartbeat is controlled by electricity. AC will get you because your heart cannot beat 60 times a second. So normally if you get into AC and it goes that path, your heart could go into fibrillation, right? Because it gets out of what? Sync. Yeah, your heart can't beat 60 times a second. Mine's usually around, depends on what I'm doing. When I'm at rest, mine's probably 60 times a minute, right? Leg to leg, this takes it through your kidneys, right? I mean, foot to hand, or either one. Hand to hand, foot to foot, right? You understand that? The other one is actually pretty neat. Shows you the resistance, different resistance, typical resistance in current flows at 110 volts. So ear to ear is very dangerous because this is very, very thin skin, right? Low resistance right here. Dry skin, now 110 volts. This would be, dry skin would be what? 1.1 milliamp, which is dangerous, but it might not be fatal, right? This shows this bit. Dry skin has a lot more resistance than in cuts. Cuts, basically, if you got a cut, then you've lost your what? Resistance. Yeah, you've lost that resistance. Now all you got is the resistance of your body, right? I mean, your muscles and stuff like that. So be real careful on that. If you got cuts, be real careful about around voltages, right? We had my wife was cooking yesterday. We had no, I'm sorry. Yes, it was yesterday. And all of a sudden, part of her kitchen went dead. The voltage in the plug. And there was a wall outlet over here on one side that started arcing, which had nothing plugged into it. Now, how could that happen? Yeah, a lot of people don't understand how houses are wired. So our houses are wired in parallel. So what we have is we have all these outlets, and then they're wired in parallel. And then this will go back to a circuit breaker or a fuse. We don't see many fuses anymore. But the way they wire the plugs is depends on the electrician. But they give you the ability to wire the plugs. It's got two screws on each side. And what you do is you bring in one on this one, and then it's got a metal rod that takes it together. And so most electricians will send it out this. So actually, the parallel circuit is fed through each one of your receptacles. That makes sense? So that means the first one that comes in down the string, this little screw right here is handling all the current of everything that's plugged in all the other outlets. And if it gets any resistance in it, then what's going to happen? Between this connection of this wire wrapped around this screw, and then this wire wrapped around this one that feeds everybody else. So we're talking about this guy right here. That screw right there gets some type of resistance in it. I'm trying to run a crock pot, I'm trying to run a griddle, and then I'm trying to run an air fryer off these plugs down here. This guy gets resistance in it. All right, you understand? Well, no, it's not going to keep the breaker. Breaker don't care. It's not going to get over current. This is what happens. Where's my drawing at? I don't know. P, which is the amount of power we produce, P is equal to I square R. Well, as soon as I get a connection, I add what? As soon as I get a bad connection, I add what? R, right? You understand? I square R, what is power done in a resistor? What do we get? What type of power do we get out of a resistor? Heat. Now we're trying to run all that current through that resistance, even though it might be 1 ohm, right? You understand? I'm trying to get 10 amps out of that. I square R. 10 amps squared is what? 100 times 1 ohm, right? You understand that? That's 100 watts worth of power. Everybody ever touched a 100-watt light bulb? What happened? Burns you just like that, right? You understand? So what did it do with all the plastic that was on that outlet? Melted it. Now I have no connection at all, right? You understand? So the outlet literally melted because that's where it was arcing at, right? You understand? So it's very, very important. The way houses are wired, good electricians won't jump them like that. They'll run what we call a pigtail and hook it on there. But most electricians, that takes time, and they'll just string them like that. You understand what I'm saying? Yeah. So of course, when I took it off, what was the first thing I did? No, I didn't get shocked. What was the first thing I did? First of all, I checked it with my meter, right? I saw the top one had nothing on it. The bottom one still had 120 volts. Didn't blow a breaker because I didn't. In fact, I went down because I added a watt in. I added another R in series. So no, it didn't pop a breaker. That's what we thought first. But we went down to the breaker panel. It was nothing popped. So checked the meter. Went back into my panel box. Turned it off. Came back in there, took my meter and put it in there and verified it was off, and then I replaced it. Everything's fine. That was my grandmother, my wife's grandmother. Well, what had happened is that she had a refrigerator that, well, of course, anytime we have metal, the metal's supposed to be grounded. Right? I understand that. In our house. And what is the ground in there for? Well, first of all, anytime I put magnetic fields through a chunk of metal, it's going to induce voltage on it. So what that means is we got AC, and AC is constantly changing. So if I didn't try to get rid of that charge, your metal appliances they would get a static charge to them, which means I'd go over there and touch them and it would zap, right? Understand? Another thing that we have is that we have 2 wires that come in. One of them's called neutral, and neutral is reference to earth ground. So we actually have 3 wires. We run a true earth ground. Then we run 2 wires. One of them electricians called hot, and one of the electricians called neutral. NEC don't use that. They use the non-carrying, they say the ungrounded current carrying conductor and the grounded current carrying conductor. So the difference between neutral and ground is the ground is not supposed to carry current unless something unless something goes wrong. So what happens if this hot lead, which has got a little bit of insulation on it, If it comes in contact with this, instead of my whole refrigerator becoming electrically hot, it pops a breaker because now there's current flow in the ground. The ground's not supposed to have current flow in it, right? So it creates a short circuit. Well, what had happened is that my grandmother's son came in there and used a extension cord to power up a refrigerator because it wasn't by a plug. And he cut the ground off the plug because it was a 2-wire plug instead of a 3-wire extension cord, and he plugged it in backwards. So that means this guy right here that came into the metal now was connected to the hot, and the hot was connected there. We left the ground, so he had no ground, so even though he wired the thing backwards, because he plugged it in backwards, right, he made the chassis hot, right, you understand? So she got in there cooking on her stove, and she had the stove, and she opened the stove, and when she leaned over, her rear end hit the refrigerator and shocked her.
Wow.
Bless her heart.
And so I went in there and pulled out the extension cord and turned the plug around for the refrigerator and plugged it in right. And her son Billy says, it makes no difference, it's AC.
Is that why on the plug, one of the bones?
It's round, that's the ground.
Right, and then the
But-
other one can be bigger.
Right.
And one is smaller than you don't.
So if it's not wired right, it's still up to the electrician to wire it right. So we have what we call double insulated devices. These are guys that are within an insulator, so plastic stuff may not have a ground on. So my hairdryer don't have a ground on. Why? Because it's double insulated. It's inside an insulator, right? You understand? So that plug can usually be plugged in either way, but they've got a ground fault on it too. We'll talk about that. So the problem is that when we get out there, the electricians, it's up to them to make sure they wire the neutral to the metal, and then the hot, the black lead to the circuit. And then if they wire it up backwards, the first time they put the breaker, it's going to pop the breaker because they wired it backwards, right? You understand? If you leave off that ground connection, right, you understand, then there's no reference to pop the breaker, and you can have the outside chassis can be hot. So you'll see that all the time because a polarized plug, it can only, a 3-prong plug can only be plugged in one way as long as you don't break the ground off. People do that, right? Because they'll have a non-polarized plug, or they'll have an extension cord that's not grounded. It won't fit in the extension cord anymore. So they'll do what? They'll break that ground off, and when they break that ground off, what can they do now? They can plug it either way, and that's dangerous. Yeah. So yeah, I put a big light bulb on there and showed him how it came on, and I tried to explain it to him, but I don't think he ever believed it. So this was an interesting chart when I saw this, that women and men, it also depends on the gender. I guess men have been shocked so many times. Well, no, they're more.
Oh, really?
Yeah. Because usually our calluses, especially on our hands, are more in the palm of the, we're talking about the fingers, would be slightly different. So what's so interesting is that slightly sensation, 1 milliamp for a man, 600 micrograms for a woman, right? This is typical, guys. This is not standard. So, guys work with our hands all the time, and so we build up bigger calluses. But, if you've got a woman that's been out there, a female out there a long time, Brittany didn't want us to use the term female. Why? Because females are all through different species. She didn't like being compared to like a dog. So she wanted to use the term women. So we was in that thing. But this really amazed me that men have a higher threshold to electrical shock than women. Typically, I should change that to typically. And also, what was interesting is that DC is is a little more dangerous. AC is a little more dangerous than DC, but it also depends on frequency. Because we create what we call a capacitive effect. We can actually couple through the skin like a capacitor, which is, if you understand AC, you understand it. So the higher the frequency with AC, the more dangerous it is. But this was an interesting chart, right? A threshold of pain, around what? For DC, around 5.2 milliamp per min. Pain in the voluntary muscle control maintained. Then loss of muscular 60. So anything in here, guys, this is bad, right? Difficult breathing, and then possible heart fibrillation. And AC, guys, AC don't matter the frequency. Once you get into 100 milliamps, and it goes through your heart, hand to hand would be very, very dangerous, right? Because now your heart's going to try to beat at the frequency, and it can go into fibrillation, which means you're what? Your valves and your heartbeat are what? Out of sync with each other.
Is AC more dangerous because of the direction or what?
Well, what happens with AC is we have a device called a capacitor. So a capacitor consists of two conductors separated by an insulator. Well, what happens in a capacitor will charge up. We can put DC on it, but once it charges up, it becomes infinite. What happens on AC is if I come over here and do this, then it'll pass through there and it'll come on the different side, on the other side. Literally come on the other side. How much gets through there? The opposition is called X of C, and it's equal to 1 over 2 pi FC. F stands for frequency. And this is opposition in ohms. So you can see as frequency goes up, the opposite. So I'm a capacitor. This is my insulator, my fingers, right? My conductor I'm in contact with, and my conductor inside that's in my metal, so I make up a capacitor. Capacitor will pass through an insulator. AC will pass through an insulator. It will pass through an insulator. Depending on what? Well, but depending on what we call the capacitance, which don't mean anything, but this guy right here stands for what? Frequency. So the higher the frequency, the more it couples through my skin through a capacitive effect. So you see what happens, the higher the frequency. So this is 10 kilohertz, this is 60 kilohertz. 10 kilohertz is more dangerous than 60 hertz, which is what Alabama Power. So normally we won't have to deal with 60 kilohertz. There's very few industries you'll go that'll have that high frequency. But if you work for a TV station where you're putting out hundreds of megawatts worth of power on that antenna out there, especially ones that still transmit through the air, are shooting up through those big dishes that's shooting up to these satellites. That's real high frequency, guys. And there's a lot of watts out there too. And that stuff will get you. So whether you understood that or not, but it's dealing with the frequency. The higher the frequency, the less opposition our skin produces. Y'all had AC yet? I know y'all don't have to take AC. Now, if you take industrial electronics, you'll take AC. AC and DC are not the same. They're the same if you run them into resistors. If you run them into other components like capacitors and inductors, everything changes, guys. I mean, So here's our two safety standards, the 910. This is it, guys. This is occupational safety. There you go. And you can see it's big. I don't know what, that's probably not, I know that's not the newest version. So that's 8 years, but it'll give you an idea. Of course, here we're dealing with electrical safety. That guy covers safety, right? You understand that? So it's got all different types of trades in there, and it's got the safety rules that cover the safety procedures that cover those trades. So we're
OSHA 10, it covers.
OSHA 10's in there somewhere. OSHA 10 is an electrical certificate. Electrical safety. So the OSHA, what they got, OSHA 30 and OSHA 10. But you have to renew
Every year.
every year.
I think every year, well, the
Okay.
job I worked at, we did it every year.
I think it's a certified instructor, which is what Boyd and Nancy are, to actually offer the OSHA 10. I think they got to do it every 2 years to be recertified. Is it the law? Is OSHA 1910 the law? Is the National Electrical Code the law? Could be. If the authority having jurisdiction adopts it, right? And of course, 70E, which is electrical safety, is it law? Only if the what? So OSHA is law, right? And then only if what? Only if adopted by the local authority having jurisdiction. And this is also true. Yes and no. So any employer, anybody employed by the Department of Energy, this is law. No for everyone else. OSHA has not adopted 70E, however, 70E employees need performance required in 9. So what that means is 70E has not been adopted by OSHA, but it helps them meet the requirements that OSHA requires. So 70E is the big thing, guys. I mean, odds are now, if you go to work for a big company, you're going to have 70E standard, especially if you're in an electrical trade. So electrical safety is in subpart S, that big old book. National Electrical Code, National Fire Protection Association 70 is a legally adopted standard for safe installation of electrical wiring and equipment in the United States. So basically it doesn't cover you, it covers your safety, it covers how to safely install stuff, right? You understand? So you don't cause fires. 70E, which is the electrical safety in the workplace, standard of the National Fire Protection Association. This document covers electrical safety procedures for employees. That makes sense. Are you okay? And they typically call it 70. They don't call it now. So that's the book we just showed y'all, right? And then this is the I should open that. So here we go. So this is access. So that's I'll put the link up there so you'll access. This is everything that's logged in this book. You see what we're going to deal with primarily in here is subpart S. Which is what? Electrical safety. And you can see it's not even half filled up yet.
Say revised. I mean, everything.
It says, no, it says reserved.
Oh, okay.
So these are the ones that's in there now. Electrical utilization, general, wiring design, wiring methods, special, specific purpose equipment, hazardous locations, special systems. And then they didn't do these. Now, why they skipped over these, I don't have any idea. But you can see they go all the way up to 400. And then they've reserved all the numbers between them, right? You understand? For later modification. Okay. So you can click on this, and then this would take you up to the actual standards themselves. Okay. So that link's in there for you. That should be on the website. This you can't leak off the PDF, but that should be up there in safety. So we'll deal with these right here. So 9 electrical Top 308, safe installation, workplace practices, 335, definition, references, document.
Is this, how, what,
I don't think I think I have it up there as a 3. So normally what we try to do is we try to put it up there as a full page, and then we try to put it up there as 3 PowerPoints per page, which is good because if you run that off, then you got now the slides make sense, so you can make notes. So let's make sure this is up there. Blackboard has been so slow lately. Of course, it crashed a couple weeks ago. During the weekend, too. So this should be the same PowerPoint that we're looking at. Sure, it's not going to have the color on it. Oh, I thought it did. No, I don't have it down as a 3. I'll put it up there as a 3 per page. I just got the whole thing. And usually I do it in black and white unless it's got white background, white text on it. That way. So who is a qualified who's a qualified employee? Somebody that's been trained or maybe certified, right, in doing certain things. And then we have what we call an affected employee. What would be the difference? Affected. So if I had, I was in maintenance, and I was qualified to work on a piece of equipment, and then I had the operator of that piece of equipment, and I needed to shut it down. Well, what would the operator be considered? Would they be qualified to work on it? No. So that would be what we're calling it. Affected employee. They would be affected if I worked on it, right? You understand that? It all depends. On what they're doing now is that a lot of your operators can do basic maintenance, not real maintenance, but basic maintenance, right? You understand? Like over there, if something gets jammed up, knowing what to do if it gets jammed up, right? So there's kind of a cross here. On our new generation, of employees. Premise wiring, connecting the supply, other wiring, and optical fiber cables. And these are qualified and unqualified employees, right? Does that make sense? Are you okay? Does not, so this doesn't deal with how it's generated, how it's distributed on the station. Not really important to know that, because I could always do what? Look it up, right? Qualified person. So we hear one who has received, and Michael said it just right. One who has received what? Training, and also has demonstrated, right, the skills. and knowledge in the construction and operation of electrical equipment and installation and the hazards involved. And what's a hazard? Something that has the potential to cause an injury, right, or an accident. Employees who face the risk of electrical shock that is not reduced to a safe level in installation requirement must be trained. Occupations must be trained, other employees if they face. Now what we've done is here's the occupations that must be trained, the work of electrical. Notice we fall into that, right? Person says electrical and electronic engineers. We're not really engineers, even though we do a little design work. Electrical and electronic equipment install assemblers, electronic technicians, so that falls to us, and then of course electricians. So according to this table, you are supposed to be trained in electrical safety. Well, that's what we're doing now. So which one will we fall under it? This guy right here, right? Recognize live parts. When we talk about live parts, this is kind of misleading. We don't mean they're alive, right? We mean they're what? Electrical energy. Yeah, they got electrical energy on them, right? Determine voltages of live parts, clearance distances, and specified in this. Are we okay? That makes sense? So recognizing parts that have energy applied to them. Here is electrical energy, but what we need to do is also focus on any energy. Of course, over here we have two energies that we're using, and what's the two energies we're using on our pneumatic and electrical, right? Okay. Determine the voltage of live parts. This gets people messed up too, as they don't understand what voltage they're working on. You know, which could be very dangerous, right? Because you get into, you're working around with 24 volts, you would be different than you're working on like 2300 volts, right? It would require different PPE if it's active. You have to do different things between the higher the voltage or the higher the potential of an accident. They call it energy. They do it in calories. And it's a little math formula that they calculate. Depending on how many calories of energy that's available there, depends on what type of safety measures that you have. What energy boundaries we have. So we have basically three boundaries we'll look at. And the further you get away from it, you would wear different PPE if you was way away from it. And the closer you get within these boundaries, will specify what type of PPE you have to get. Focus on work near exposed energy or potential energy parts. Locking and tagging. Most of y'all understand that, right? What's locking and tagging? Yeah, that's got an energy source on it, right? Or source of power. We're supposed to lock it out, right? And then tag it. So are they the same? Locking and tagging are the same?
They go hand in hand.
Well, we can tag without lock, but we can't lock. We're not supposed to lock without tag. So tagging we use just to convey information. There are some, if we don't have the ability to lock out. So at my house, I don't have the ability to lock out my breaker. So what should I should I have done when I went in and tripped my breaker? I should have put a tag on it, right? Saying, of course, I'd have been upset. I didn't do that. De-energization. Well, that means we need to get rid of the sources of all power sources, right? And then, of course, if we'll have a procedure we're supposed to follow before you lock and tag. You're not just supposed to go out there and just cut everything off and tag it, right? What would you think you need to do? If you're going to lock and tag. First of all, you need to follow the procedures that are set up by your company. And odds are they're all going to follow the same procedures for locking and tagging. And what's the first thing you should probably do? No, you should tell everybody that's going to be affected. Yeah. Tell everybody that's going to be affected for you killing the power source. Right. Right. And then once you tell everybody that's supposed to be affected, then you're going to do it. Probably lock it and tag it. And then what's the next thing you're supposed to do before you get your hands in it? Well, when you lock and tag, they're supposed to de-energize. But what are you supposed to do?
Information on tag.
That lock and tagging, you're right. You should always verify.
Make sure that
Always verify. Always verify that the energy sources have been, like we talked about over there, just on the pneumatics. Just because I lock and tag my compressor, what do we got to do now?
make sure
Yeah, we got to bleed that pressure off, right? You understand? Electricity, we got contacts that get stuck. You know, that happens every once in a while. So, how do we verify there's no electrical energy? Check it with your meter. That's exactly right. So that's what I want to see. You want to lock it and tag it. And the first thing you're going to do is over there with your meter and do what? Verify there's nothing there. Where it's supposed to be. What we can do with our pressure gauges, you notice the pressure gauge there drops to 0. If I came over and looked at this, if it's not leaking, this right here can still be water. That Fanuc robot back there, it's got an extremely good seal. It's sealed really, really well. We got that robot in, and we must have ran it for 3 days with that compressor down there. And I was thinking, man, that compressor sure is silent. And then all of a sudden it kicked in. So, and that was shipping it from wherever they put it together at. So right now, how many of y'all heard the compressor on the Fanuc running? So right now, if I kill that compressor, then it's going to be all stored up, right? You understand? So I would need to figure out how to relieve that. Most compressor tanks have a pressure switch on it, not a pressure switch, a safety switch on it, right? And it's usually got something that you can do what? That you can manually pull out and drain the pressure off your compressor. Which I did. Let me tell you what I did. It's wonder I didn't get hurt. Verify energy. There it is, the next one. Verify what? And what should we do before we energize? So we should have if we got a procedure for de-energizing and locking out, we should have a procedure for taking that lock off, right? So what would be some of those procedures? Make sure you let the affected people know you're fixing to throw that thing back off, right? Make sure everybody knows, because they might be out there and the disconnect might not be anywhere around the equipment. Let everybody know you're fixing to energize it, right? Make sure all your tools and everything is what? Out of the way, right? Right? Let everybody know, right? Who can put the tag on and who can put the lock on and who can take the lock off? Yeah, the only people that should take it off is the person that put the lock on. Now, of course, every company's got a procedure that they have to follow. They can follow if something happens, right? You understand? So here, John or Joe Blow out there got in a car wreck or something and can't come in, and your whole piece of equipment is locked out. Well, there is a procedure in place, but you got to go through hell and high water to do that, right?
So everybody is working on that equipment. They got a lock.
Everybody.
They got to put a lock on it.
Everybody that works on the equipment, and we'll show y'all what we do. We have what they call expander rings, where you can put multiple, that we can put multiple locks on there with. And that's what we'll use, because everybody's going to lock out, right? You understand? And tag out. What should the tag include?
Name.
A minimum of your name. A minimum of your name. Who put the lock on there, right? And that way they know who to contact if the lock is left on there, It cannot be a combination lock. It's got to be a key lock, right? And who has the key?
You look at the box.
Oh, you have the key. It's up to you. No, you have to have the key. Whoever put it on has the key. When we worked out there, when I worked at U.S. Steel, the bosses had a key. So it's a little different now. The bosses, they had a box. They kept it locked all the time. They had a key to the box. If something happened, you couldn't make it out there, they could take your lock off. Not anymore. According to OSHA, not anymore. So now there's only one key. One key. You have the key. Nobody else is supposed to have that key. You're not supposed to give the key to anybody, right? So literally, if you gave your key to somebody and they went out and took your lock off and they got killed, whose fault would it be? Be yours. Right? So now we use a keyed lock. Why not a combination lock? Not only forgotten, but you can give them away, right? Keyed lock, one key. If you lost the key, U.S. Steel, what do? They give you a new lock. Right? If it's on there, then you cut it off, right? You understand? But they would do one. They give you another lock. Lock it out, untag it, move it out, verify that it's fixed. Depends on where you're at. You might have to turn everything back off, right? You understand that? So, overhead power lines. I need to find that video. We got a video. It's about 6 guys. I don't know where it's at, but they're moving this big old stand, and they're all moving that thing. And guess what they hit with that thing? High voltage power ladders. That's why Mr. Sanders got here. The last person that we had teaching the electrical classes, he came from Bell South. So he bought a bunch of ladders. He bought aluminum ladders for the electrical classes. Mr. Sanders got here. You know, he's a master electrician. And what was one of the first things he did? He replaced those, and, you know, well, they're still here, but now we can use them for other things. Fiberglass. So yeah, they have fiberglass ladders over there too. Illumination, you know, having the right, being able to see things, and then several of that. Okay, so 2 things they gave us. They gave us 3 things at U.S. Steel when we started it. They gave us a multimeter, Simpson 260. They gave us a pair of stake-on pliers, which were basically wire cutters, but it had the cut so you can cut screws, and it also had the where you could do crimp-on connectors. And they gave us a flashlight, and they gave us a hard hat, and they gave us the first set of steel-toed shoes with metal tarsal. You got your metal tarsal?
Here all day.
So that was the things they gave us. The first pair, if you messed them up, you'd have to buy them. Gave us our safety glasses. De-energized parts. Y'all need a break? Let's take a break. So de-energized parts. Live parts for which an employee may be exposed shall be de-energized before the employee work on or near, unless the employer can demonstrate that de-energizing reduces additional increased hazard or is feasible due to the equipment design or operational limitations. Live parts that operate at less than 50 volts to ground need not be de-energized if they will not increase exposed electrical burns or to explosions due to arc electrical arcs. So this is out of OSHA, right? Are you okay? Exposing anything below. So what 70E, you can see OSHA has adopted a lot, or 70E adopted stuff from this section of OSHA. I don't know which one. But even 70E considers anything above 50 volts to be legal. So anything above 50 volts, that's where we're going to have to consider personal protection equipment, right? Anything below 50 volts depends on the requirements of your employer. So if you went to work for U.S. Steel, you're going to have to wear safety shoes and metal tarsuls if you're in that plant. You're going to have to wear safety glasses. You're going to have to wear a hard hat, right? You understand? And I don't think they allow you to wear polyester or flame tarts too, but they might require you have a certain uniform that has certain flame retardant capabilities, even if you're working below 50 volts, right? 334 covers portable equipment, plugs and cores, reclosing circuits, and inspection of equipment. So what we're doing is we're looking at OSHA, right? First, PPE must be used when exposed. Maintenance and inspection, insulated hand glove, tools, guarding and exposure parts during work. A lot of people don't understand that 70E also requires you, if you're working in a cabinet, say a disconnect or something, and you've got a cabinet beside it, right, then you have to prevent that from getting into that section, right? So they have curtains and stuff that you have to put up to prevent that from happening too. And of course, insulated hand tools. So if you got hand tools at home that you use and they're non-insulated, my father-in-law had a bunch of wood itself is a fairly good insulator. It's what can get inside wood that causes the insulation to go down. That was what was the show with Jesse James? He wasn't building motorcycles. They were having competition to build different things, and they was trying to convert a car over from a combustion engine over to electrical. And what they did at first is they put all the batteries, the mounts for the batteries was made out of 2x4. And they left them outside, it rained, and they caught on fire, right? Because all of a sudden you introduce things into the wood. Dry wood is a pretty good insulator, but if you got anything in it, if it's got sap or something in it, then it don't work out too well. 70E, so this is what we'll get into this. So safety E, what does it cover? Shock, arc flash, and arc blast. And I couldn't find the video by the guys, but all those guys.
What's a thermal burn?
Well, thermal burn would either be called by an arc flash or what. That's what a thermal burn is. You get in real trouble when you have what we call an arc blast. This is when we have short circuits, mainly. And you got a lot of energy level there, and you got a circuit breaker. Well, a lot of circuit breakers can handle a short over a certain cycle. During that time, a lot of things can happen. Fuses don't blow instantly. They have to detect the short before they can blow, right or pop. So what happens is that energy is there, and it could cause what we call an arc blast, which means when it causes an arc blast, this is a flame that appears instantly, which is around, I think, 36,000. It's harder than the sun. So any metals or anything that you have are instantly going to do what? They're going to vaporize. And then you have shrapnel and all that kind of stuff. All that heat causes all the air to do what? Instantly. When we heat up air, what does it do? When we heat up just about any gas, what does it do? Metals. When we heat up metals, what do they do? They expand. Yeah. And so your air is expanding instantly, like in your car. So you got that gasoline in there, and you fire that gasoline off, and the gasoline has been turned into vapor, right? You understand? It's not like the gas in your tank. It's vapor. It's a gas. And then you fire that thing up, it creates an extremely hot flame. And what happens to the air that's been sucked into the cylinder? It expands, right? When it expands, it creates a pressure. When it creates pressure, it creates a force. A force tries to create motion. So if you got something that's going to move, it's going to do what? It's going to move if it's got enough surface area to overcome your friction. So this is the same thing happen when you have an arc flash. It creates a pressure wave that comes out. They was talking about that big bomb that they dropped the biggest non-nuclear bomb they have. And it's basically, that's what it kills people. The bomb itself don't kill you. It creates an extremely lot of heat that creates a pressure wave that comes out and just blows you apart. Yeah, it expands so fast, and it will literally blow. It's such a fast wave that it literally blows people apart. It's not the shrapnel coming off the bomb, right? It's what? It's the pressure wave created by it. It always amazes me when they show the thermal, and that's what nuclear explosions do. It creates a shock wave that kills people, plus a lot of other nasty stuff. So that's what an arc blast is. So blast could cause thermal burns, but it also could cause a arc blast, which can cause big problems. So this is basically what they deal with. Dangerous conditions such as contact of equipment failure can result in either shock, an arc flash, thermal burns, because that arc flash is going to put out a lot of heat, right? You understand? And then arc blast, which could basically knock you off things and give you problems. And this is what 70E covers. Doesn't cover electrocution, it covers shock. Because if you don't get shocked, you're going to get electrocuted. So what can you do to prevent from getting shocked? If you do things to prevent from getting shocked, you're not going to get what? Electrocuted.
What again? It's a water pipe? Is it a hose?
I don't know what it is. That don't look like what it's hard to say what it is. These could be off a welder. I mean, I can't tell what it is. We got videos on this, and we'll look at these. Arc flash, electrical short circuits that occur when air flashes from an exposed electrical conductor to another conductor or ground. An arc blast is the pressure wave that's created by all that heat, right? That makes sense. So you can't have an arc blast unless you have an arc flash. Are we okay? Concentrated energy explodes outward. Highly intense flash temperatures can reach 35,000 degrees. I forgot how hot the sun is, but it's not that hot. I should have degrees out there. So basically, nothing we know of is not going to be disintegrated with this, right? Understand? So we got this pressure wave coming out. Can create waves that reach 300 pounds per square inch. I've got a lot of square inches, right? You understand that? That's 300 pounds per square inch. If it's pushing against a flat surface, and if I push that against 2 square inches, then it's going to be 400 pounds of force, right? You understand? 3 square inches would be 600 pounds of force, right? Bad stuff. Vaporizes conductors in copper and explodes particles like buckshot. So these guys right here are bad. Arc flashes cause severe burns, broken bones, disease, damage, hearing loss, brain, internal injury, punctures, and lacerations. And they could definitely cause death. The problem we have, and there's nothing we can do about it, if you get hit by something real hard, you usually go like that, right? So what's probably going to happen? You're going to breathe all that garbage in. Burn your lungs. Cause of arc flashes, number 1 on the list is what? Yeah, number 2 is number 3 is problem. Drop tools. Right?
It's like a blast.
Yeah, it's a blast. I mean, it is a blast. And we can look at some of them.
You can fix that in welding. normally they call it an arc because it is
but it's not a blast. It's a control. It's a control arc. But think about the heat you get off that thing. I mean, it melts metals, right? You understand? So we're talking about extremely hot, a lot of heat that we can get off of electrical short circuit. I don't think I've downloaded it. I can't find the one. So Cece got her she got her long certificate in welding. And then she got an AOT, which is a major minor. She minored over here. She decided she liked it so much, she decided to come into our program too.
Like one guy, he had took a welding rod, and he had in the electro hose, he had just took the arc, and he put it to his hand, and shot himself. Yeah.
Now that's a lower voltage too. Well, once it strikes an arc, it's pretty high voltage, but it's got a lot of resistance in the rod, so the voltage drops instantly, right at the tip. There's a lot of current out there. So let's go to YouTube and just search for arc blast.
So you got
She'll have an AOT in welding, and then she'll have this is a pretty interesting. I don't have the sound. I don't think this actually has sound or not. So this is an overhead camera, and he's racking a breaker. These big old circuit breakers that handle this high power, they're in a rack. You put them on there, and then you clamp it in. Now you notice this hole in the floor. This is where he's supposed to be racking the breaker at. So you have a thing that you spin, and it literally moves the breaker back into the rack. You're supposed to be racking through the door.
So he got the door open.
He got the door open.
So that's number one.
Number one, yeah. You can see him racking it in. I don't know if this guy made it or not. He is going to put down, right now he's got his face shield up. Huh? No, the other guy's going to be lucky. Or lucky, he's blessed. I think there he is. Here, see, there he goes. Now, so he put his face shield down. He's got his earphones on. Not his earphones,
So what is he doing?
Racking a breaker. That's an arc blast and an arc flash.
Oh, he died.
I don't know. They don't show anything else.
Well, that man made it.
Racking a breaker is the way these big breakers work on now, they actually make a connection in the back of them. If they need to work on them, they can and it brings them out, and then they can put them on and put it on a big cart to go work on them. When they come in and they rack them, they put them back on these rails, and then they screw them in. So they have a worm gear down there, and they screw them in. They're supposed to be closing the door and then racking them in with the door closed. He racked them in with the door open or something. So
the door has some sort of protective.
Well, it's a door, yeah. It's got. So there's all types of arc flash and arc blast, electric arc flash, and actually this is just a bunch of them right here. What they're trying to do here is they're trying to put in a circuit breaker. Y'all see that? line where a tree fell across the two places. How long is it gonna last? We've already seen this. I don't think this guy right here makes it either. I don't know what he's doing. It's not a real good video, but he's doing something he shouldn't be doing. And he don't have any, don't look like he's got on any PPE at all, does it? Is that him on fire over here?
Oh, wait a minute.
Forklift. Oh, this is the one, guys. This is the one. So here's this big old stand they're bringing around here. And there's 1, 2, 3,
They're gonna hit the line.
4. There's 4 guys.
All of them.
They're gonna hit the line, and they're gone. Boom. Notice this guy's burning.
So they can't let go?
No,
Is that what happened?
yeah. Look, this guy's smoking.
That's
Holy
what they said when you get
crap.
shot, you get like a piece of wood, it hit somebody.
So that's 4 guys, just like that, just by not paying attention to what they're doing.
So I know a kid that did that, Johnson touched power line. What happened with the three internally? Right?
Well, you can have to bring up my PowerPoints. Give me something I can. So if we was to look at the, and there's a video of wrecking a breaker. That might be where I looked at. So. So you got the big power rails in the back, and they're usually vertical. So they look like this. And then on the back of the breaker, you've got these big old blades that come out that are clamped together. And then they'll have a little thing right here. So what happens is when these slides over these things, they literally spread themselves apart and really clamp onto that. And then what you'll have is you'll have rails, and your big old breaker sets out, out here. And then you'll have the breaker. Well, these things have to be worked on. So they got to get that thing out. So they'll have a screw down in the bottom, and they turn that handle and literally do what? Screw it out until they get it far enough. And most of the time they'll have a cart that they can line up, and they'll pull it in there, and they'll pull that thing. Once it breaks loose off the screw, they'll pull it out onto that cart, and then they take it off and work it. So that would be what we call unracking a breaker. Racking the breaker would mean you bring your cart in, you push it on there until it engages that screw, and then you do what? You screw it in there slower, and it comes back, and when it hits those big old power rails back there, it'll open them up and then slide on to those big power buses back there in the back. That's where you
What
put.
do you think may have gone wrong?
Well, they didn't have the things wrong, or they was putting in too much pressure and the flaps got bent over, or there was a short out there on the line. There was a short out there, and it wasn't the breaker's fault, right? You understand? So the breaker kicked and burned up. Some got burned up in it, and they came back and they fixed it. And when they put it back in there, that short was still out there in the system. And as soon as it came on there, as soon as those rails touched, it created an arc, right? You understand, and it blew up. So to get an arc blast, you got to have a short circuit somewhere. You got to have two wires touching out there, or you got to have one of your wires touching ground, right? Because we distribute power relative to earth ground because it's a lot safer. But that can cause us what? It can cause us problems. You know? So we got a short circuit out there somewhere. And then what happens as soon as it hits, it creates that heat. It welds the metals on there, right? You understand? And then after that, it's just. So the way the breaker pounds are set up now, they rack them through the door. So they actually close the doors and latch them down. And then they can rack them through the door. So if you have a blast, then it's going to come into that door, right? You understand? It might blow the door off, but it's a lot better to be hit by a door than it is what you saw there. You know? Yeah, we got one video I need to show y'all where they start having an arc, and it's over in Russia somewhere, and there's a bunch of snow out there, and these guys are throwing snow up inside that circuit breaker to try to put the arc out. They don't get. Well, it does. But that's one of those things where you are blessed. They didn't get killed. I don't know how. But you're throwing water into, water, distilled water is a real good insulator, but we don't see much distilled water out there. It's got all this garbage in there that, so water itself is not a really good conductor, but it's more conductive than we are. So that's why we got to really be careful. So we put water, if you put water in a battery, what type of water should you put in there? Distilled water. Because if you don't, all that garbage is going to settle and it's going to short out your cells. A lot of the cells get shorted just because you put regular tap water in there. Now they make it conductive with acid, but they're controlling the conduction then, right? You understand? So distilled water in your batteries, but so that might have been the racking the breaker video. That's it. So when the rest of the guys come in, we'll talk about what we need to do about lunch. I know this class goes to 1:30, and that's the same video we've already watched. But you can't see them actually racking the breaker. So we got a leak. I think one of these disconnects is leaking a little bit. That's an arc flash, but that's a dummy. That was a demonstration. 20 kilovolts.
Got the glove though, bro.
Look at the glove.
Got the glove.
Well, every once in a while, you'll see tennis shoes where they've had a wreck and you see people's shoes out the road. You ever seen that? A one-hand rule, everybody understand that? Can you see what he's doing?